So we'll look at a typical problem in classical physics using Euler-Lagrange method. A mass small m is free to slide on a frictionless table and is connected via a string that passes through a hole in the table to a mass big M that hangs below. Assume that big M moves in a vertical line only, and assume that the string always remains taut. A typical first question will be write the Lagrangian for the system. So as usual, we write first the potential energy, kinetic energy, and we take the difference to get the Lagrangian. So let's start with the potential energy. The small mass m is on the horizontal plane, so it doesn't have any gravitational energy. And the big mass m has a gravitational energy. So that's the only potential energy which enters in this problem. Choose a reference for the potential energy such that it is 0 at the table, but that doesn't matter here because we will only take derivatives of the potential energy in the Euler-Lagrange equation anyway. So for the kinetic energy, we have the kinetic energy of both mass. So for the mass big M, that will just be half m v squared, and the velocity is the time derivative of L minus r, because L is the length of the rope and it's constant, so its time derivative is 0. We also have the kinetic energy for the small mass m, and for this one we see it's relevant to use polar coordinates. So we have small r for the distance to the hole and theta for the angle, and in polar coordinate the velocity. So we get the Lagrangian, which is the difference between kinetic energy minus potential energy. A second possible question could be identify a cyclic coordinate and write the associated conserved quantity. So we see that theta is a cyclic coordinate because the Lagrangian doesn't depend on theta. It depends on theta dot, but not theta. Therefore, the associated canonical momentum is conserved. We recognize the angular momentum, which is conserved in this case. So alternatively, we could have asked, show that m r squared theta dot is conserved, or show that the angular momentum is conserved. So whenever we ask, show that something is conserved, the first thing you need to think is to identify a cyclic coordinate and calculate the associated canonical momentum. Alternatively, you can also use the Euler-Lagrange equation, but it's usually faster to use cyclic coordinate. And then another question could be find an equation of motion for r and theta using, I don't know, Euler-Lagrange equation for r coordinate. Just have to use our expression for the Lagrangian and compute. Finally, a last question could be find a condition for r and theta dot, the angular velocity, such that the small mass m is following circular orbits. So you need to realize that for circular orbits, the radius doesn't change, it's always a constant, so all its time derivative are 0. That means that r dot dot has to be 0, and therefore we have